Okay, so welcome back. Let me just write here, because I think this is intended to be a week from now if you're keeping up on the schedule of the lectures. So your first midterm is going to be on October 23rd. That's a Friday. I'm going to I'll put up a review sheet on Canvas by the Sunday before, which should be the 18th. And there is going to be a small homework assignment due on the 25th. Okay? Same format, group homework. Okay, so where were we last time? So we had kind of come up with this fundamental definition of cardinalities of infinite sets. So we had the cardinality of A is the cardinality of B. Well, and this definition also works for finite sets if there exists a bijection from A to B. Okay? So if A and B are finite, this is kind of like we proved this, or this is a theorem. Right? Because we define cardinality to be the number of elements, and then it turns out that if you have a bijection, you get the same number of elements. Okay? So then we said that A is countable if the cardinality of A is the cardinality of N. So in other words, is there a bijection between the elements of A and the natural numbers? And then we saw some examples of this. So we had, well, obviously N is countable. This is the same cardinality as the integers. This has the same cardinality of the products of the naturals, Cartesian product of n cross n. We'll see that there's more. So this will be, actually I think on this kind of small homework assignment will include a proof that the rational numbers are countable, so they have the same cardinality, there's many rational numbers as integers. There's more countable unions of countable sets are countable. So if I give you something like the union from I equals 1 to infinity of the a sub i's, and the a sub i's are countable, then this is too, and A is as well. So I won't prove any of these right now in this lecture. They're good, if you want some kind of more things to think about, I would try showing some of these statements. Again, in all cases, you have to construct a bijection between the natural numbers and whatever set that you want to show is countable. Okay? So instead, what I'm going to talk about is, well, at this point, you might be wondering or saying to yourself, you might think that every set is countable, right? That there is a bijection from n to any infinite set, right? Since we've done pretty well at showing a lot of sets which, like the natural numbers cross the natural numbers or the rationals, they seem so much larger than the natural numbers, and it turns out that from this perspective, they're the same size. So you might think there's a bijection from this to any infinite set. But shockingly, I'll say, this is not the case. This is not the case. So, in particular, we're going to see that the natural numbers have cardinality strictly less than the real numbers. Okay? And the way that we're going to do this, so we prove this by contradiction. So we're going to suppose there exists a bijection and get some false conclusion. So this is, maybe I just want to give like a little aside or sanity check, or, you know, you should test how, if you like this class right now. So this is a good test. So this is essentially completely due to Cantor. I'm going to say this is a good test to see if you'll like math. You know, that, or this certain type of math that we're kind of first encountering in this class. But, you know, pure mathematics, I'll just say, doesn't get much better than this. Okay? Like, Cantor's proof that the natural numbers have strictly less cardinality than the reals is pretty much as good as it gets. So I hope you like it. That's what I'm trying to say. Much better than this. Okay, so we're going to rely on a fact about the real numbers. So I'm just going to recall. I'm not going to prove this. In fact, you know, we haven't really defined what the real numbers are, and it will turn out that a big second half of the class is giving, you know, an adequate construction of the real numbers. Okay? But we're going to just say that the real numbers, we're going to identify them with decimal expansions. So every real number has a decimal expansion. Okay, so let me just write this out. So you might have something like 3/4, which is 0.75. Or you might have something, you know, that's a rational number. You might have something like pi, which is 3.14. I don't know too much of it. There we go. I guess I could have looked that up online and seemed very clever to everyone. You can also have infinite expressions that are, right, so not every rational number has a finite decimal expansion. You can have something like 1/3, which is 0.3333. Or sometimes we just write 0.3 repeating. So it is true that every rational number has a decimal expansion with a pattern. So at some point the digits will just be some repeating pattern. So the pattern for 3/4 is just 0, 0, 0 after the 0.75. So there is a little problem, which I think probably came up in the first homework assignment, which is that they're not unique. So some decimal expansions aren't unique. So in particular, you might have something like 1/2 being 0.5, which is also 0.4999. Okay? Or you might have, I can just keep going here, 0.2, 0.199. Okay, it turns out that this is the only kind of bad thing. So this is the only way you get non-uniqueness. And what we're going to do, just to make the proof slightly simpler, is that we always choose the one with 9 without any infinite 9s. So always choose without 999 repeating. Okay? This isn't a big deal at all. It will turn out there's only, the fact that you just have to make a choice between two things means that it won't really ever come up in the proof, but we're just gonna, to make it simpler. So another thing that's gonna make the proof simpler is that we can notice that there's a bijection. So there exists a bijection from the open interval 0, 1 to the real line. Okay? So maybe I'm just going to pause here. I'd like you to just draw a graph of what a possible bijection would look like so that we can see that we're on the same page. So I'll go one better, not just draw a graph, but give you a formula. Okay, so f of x could be 1 minus 2x over x times x minus 1. And, kind of where this equation came from is I want this function to blow up at 0 and to blow up at 1. So it turns out what the graph of this looks like something like this. And then over here there's some discontinuities. So I think it's something like this in total. So notice this is not an injective function in general, but when I restrict to 0, 1, it becomes injective, and also it's surjective. Okay? So now what I can do is, it's enough to show that the cardinality of n is strictly less than the cardinality of the open interval 0, 1. Okay? So again, this just makes life a little simpler. We only have to deal with real numbers between 0 and 1. So when I'm doing decimal expansions, I don't have to worry about a number like pi where there's something before the decimal. And it's a bijection, right? So the cardinality of 0, 1 we just showed is the same as the cardinality of r. Okay, so what do we do now? So I'll just write this as a theorem and attribute it to Cantor. So there is no bijection phi from the natural numbers to 0, 1. And if you think about it, this is really saying you can't count the elements of 0, 1, right? Because what would counting be? Well, you'd say, okay, this is the first element of the open interval 0, 1. This is the second element. This is the third. That would exactly be a bijection from the natural numbers to n. Okay. So let's do the proof. Okay, so we're seeking some sort of contradiction. If we assume that we have a bijection between these. Okay, so let's suppose that there was one. Suppose there exists the bijection phi. So what would phi look like? Okay, so, well, maybe phi of 1 would then be some decimal expansion, right? So let me just do, for example, phi of 1 might be, 0.2000. Phi of 2 might be 0.565656. Phi of 3 might be some weirder thing with not an obvious pattern. Well, I guess this has an obvious pattern, but it's not repeating decimals. Okay? In general, what we have is that a bijection between the natural numbers and 0, 1 would mean that we would be able to write down a list of decimal expansions, and every real number would be on that list. Okay? So what we're going to come up with, so the contradiction, is going to be we can find a real number which is not on this list. Okay, so that's kind of the amazing trick, right? You give me a list. We have no idea what this list looks like, right? I'm just going to emphasize this. We don't know the list because we don't know if what this function, is at all. But we're going to show that there's a real number not in the image of the list, that this function is not surjective. Okay? So let me just give you some notation. Because we don't know the list, we're going to have to come up with some notation to describe what the elements look like in the image. Okay, so phi of 1, I'm going to write as point A11. Maybe I'll leave out the comma. A11, A12, A13, A14, and so on. Okay? Phi of 2 is point A21, A22, A23, and so on. Okay? And I hope that the pattern is clear. So if I had phi of I, for the ith, natural number, I would get AI1, AI2, and so on. So Aij is the jth decimal, or the integer in the jth decimal point. Integer in the jth decimal place in the image of phi of I. Okay, so what you can imagine is that what you get from this is a whole kind of, it's a quarter of the xy planes. I mean, you should see this is very similar to the product of two natural numbers. And every point in here corresponds to one of the decimal places in the image of an integer, or of a natural number. Okay, and so maybe I should say where these are. So Aij is just a digit, right? This is in 0, 1, up through 9 for every I, j in the natural numbers. Okay, so any list is going to look like this. And now given this list, we now come up with the number z in here that isn't on the list. And that will imply not surjective, which is going to be our contradiction. Okay? Because we assumed that it was a bijection between natural numbers and R. Okay, so what do I have to do to come up with a z, which is definitely not on this list? Well, z is going to be defined, well, it's a decimal expansion, so I'll just write b1, b2, b3, ... And here's how I do it. This is called Cantor's diagonalization argument. So I look at the diagonal, and I use that diagonal to define my b. And I can do this in a bunch of different ways, it turns out. So b I is defined to be 3 if a I is not equal to 3, and 4 if a, I is equal to 3. Okay? So clearly this is in the open interval 0, 1, right? It's a decimal expansion just with 3s and 4s. Okay? And you can imagine if you have this list, you're going to easily be able to define this z, right? You would just go to the first term. If it's not a 3, you put a 3 there. If it's a 3, you put a 4 there. Then you go to this one. You say, same exact thing. If it's not a 3, I'm going to put a 3 in the second place. If it's not a 4, I'm going to put a 4 in the second place. Okay? But why is z not on the list? Okay, so I'm going to pause here. Please take a couple minutes. Think about this. Okay, so let's see why this is. All right. So let's suppose it is, right? So why is z not on the list? If it is, then there's some k, so there exists some k in n, so that phi of k is equal to z. Okay? So what does that mean? Well, phi of k I wrote as point AK1, AK2, AK3, and this is equal to point B1, B2, B3, up through BK. Maybe I'll put AKK here. Okay, so if this is in the image, then the two decimal expansions would be equal. Well, but when are two decimal expansions equal? They have to match every single term. And we explicitly chose B so that AKK is not equal to B sub k. Okay, so what does that mean? Well, we said that there's some decimal expansion which mapped onto this B, but we chose the B so it exactly wouldn't match up in some slot with every decimal expansion on the list. So, contradiction. This is not going to happen. Okay, so that's Cantor's diagonalization argument. I just, this is really something that's worth thinking deeply about. Tell your friends. Parents. Dog. Okay, so I want to tell you a couple more facts about... well, let me just say the way that people kind of say this is that they say R is uncountable. Okay? So this is what we just showed. So there's a couple things that you can kind of get from this with similar arguments. So remember we showed that earlier, or at least I sketched a proof that n cross n is countable. Here. You might ask, what if I had, n times n times n? Okay, the same exact proof that I gave is essentially going to work. Okay? So this is countable. It turns out a finite Cartesian product of countable sets is countable. On the other hand, you can look at the Cartesian product. I'll just do like the set containing two elements, 0, 1 times 0, 1 times ... So now I'm allowing an infinite Cartesian product of just two element sets. This is uncountable. Okay, and the reason, well, this infinite Cartesian product, so maybe I guess I'll write it in the correct way. I equals 1 to infinity of 0, 1. Okay. This is essentially the same as sequences. Actually, in this case, it is identical to sequences in zeros and ones, right? So a typical element here looks, I can identify it with a decimal expansion, 0.1, 0.001. Okay? So infinite Cartesian products are roughly the same as decimal expansions. You can check that Cantor's argument works perfectly well with sequences in zeros and ones. There was no reason to have, 0 up through 9 in the argument. So this is also turns out to be an uncountable set. Also, so one more, the power set of the natural numbers. So remember, this was all subsets of the natural numbers. The power set of any set is just the set of all subsets. Set of all subsets. This is also uncountable. And I kind of gave a hint of this at some point in the earlier lectures. So we saw that P of n could essentially be identified with the real numbers using the fact that a subset like 1, 12, 18, 46 could be identified with the decimal expansion 0.1, 1, 2, 1, 8, 4, 6, and so on. Okay, so if I have a subset of the natural numbers, I can list them all out and I get a decimal expansion. Okay, so finally I'd like to give just an amazing application of this theorem. So amazing application of Cantor's work. There are many more, okay, but this is just one that's too good to pass up. So in the beginning, there's the natural numbers, which we love, contained in the integers, contained in the rational numbers, and then contained in the real numbers, right? As we've seen, this is countable. This is uncountable. It turns out that the real numbers minus the rational numbers, these are just called the irrational numbers, which we've seen, or which I presume people have heard about. So these are also uncountable. So cardinality of the irrational numbers is uncountable. And the reason for that is, well, the rational numbers is countable. If the irrational numbers were countable, then since the real numbers are rationals plus irrationals, real numbers would have to be countable. But we showed they're not. So there's an uncountable number of these. Inside the irrationals, so inside, maybe I'll call this I. So inside I, there are the algebraic numbers. Maybe I'll call this A. Okay, not very standard notation. So what is this? Well, these are roots of polynomials with integer coefficients. Okay, so what is this? Let me give you some examples of algebraic numbers. Okay, so examples. Well, first, every rational number is algebraic. And the reason for that is that A over B, where A and B, remember, are both integers, is the root of the linear function bx minus a is equal to 0. Okay? But there are also algebraic numbers which are not rational. So, and you know, the way you get this, well, here's one. You have x squared minus 2 is equal to 0. The roots are plus or minus the square root of 2. So you get that these are both in A. Okay? They're both algebraic numbers. You can imagine, well, you can do ax squared plus bx plus c is 0, where a, b, and c are integers. That gives you, we know what the solutions are. Okay, so any number which is of this form is algebraic. Okay, and well, you can go further, right? I could look at x cubed minus 2 is 0. So this gives me x is the cube root of 2. I could have some random equations. Oops, probably should have 9 minus 47x to the 8th is 0. Now I have no idea what the solutions are, but the whatever it is, the solutions are algebraic numbers. Okay, so there's just a huge number of these algebraic numbers. Okay, so then you can ask, is every real number algebraic? Okay, so i.e., is it the solution to a polynomial with integer coefficients? Okay, and that would be good for algebraists somehow, right? Because then the world of the integers and algebra would be able to handle every single real number. On the other hand, it will turn out that the answer is no. But this is hard to see. So it's hard to come up with a single example. So you should think about maybe this has to be a jazzed up version, or somehow the first time you see something like this is you show square root of 2 is not a rational number, right? That isn't too hard to see, right? On the other hand, something like pi not being algebraic, or e not being algebraic, is true. This is true, but very, very difficult. Right? You have to show that something is not the solution to any polynomial equation. You can think here, the fact that square root of 2 is not rational is like saying it's not the solution to a integer equation, like bx minus a. So this is saying it's not a solution to any polynomial equation. This took, hundreds or thousands of years of work. On the other hand, so it's hard to come up with a single example, but it's easy once you have Cantor to see that almost every real number is not algebraic. So these are called transcendental numbers. So how does this go? Well, what you realize is that there's only countably many algebraic numbers. And since the real numbers are uncountable, the transcendental numbers have to be uncountable. Okay? And why this comes from well, there's countably many polynomials with integer coefficients. This I'm going to leave for you as like kind of an exercise. Countably many polynomials with integer coefficients. You can think, well, how many quadratics are there? How can you prove that there's only countably many quadratics? And then how many cubics? And so on. Okay, so you use the fact that countable union of countable sets is countable enough times, and you'll get to this theorem. Okay? So what does that mean? If you have countably many polynomials, well, you get countable number of roots of such polynomials, so you get countable number of algebraic numbers. Okay, so I am going to, this is, enough amazing stuff for one day. So, thank you.